was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. It bursts from the sun with the power of 10,000 nuclear weapons heading straight for Earth.
Think of totally destroying the power grid of an entire continent.
Television, radio, internet, all down. So is running water, fuel deliveries, food and groceries across the globe.
These storms have a planetary footprint, and the potential for loss of life is quite large.
Within a year, millions of people are dead. National infrastructures are ruined and may never come back. This isn't a disaster film. This is a 2009 research report from the National Academy of Sciences, and some say the global catastrophe it outlines may be coming soon.
We're overdue.
Solar magnetism. Why is it so deadly and so misunderstood? And is there anything we can do to escape the magnetic storm? Spring 2013. The northern lights dazzle millions in the night skies above New York, Chicago, Washington, D.C., and across Europe. These auroras are the result of a coronal mass ejection, also known as a CME. It's a massive magnetic flare from the sun.
The extreme magnetic field is like an explosion on the surface of the sun, and it's 10 to the 25 joules worth of energy. That's 100 million times more energy than the largest nuclear device that man has ever made.
Billions of tons of solar material fired off into space, electrically charged, magnetically polarized, aimed directly at us.
These things are the size of, well, they're 100,000 miles across. They're a third the size of the sun. So it's like accelerating the whole Mississippi River and making it move at 1,000,000 miles an hour toward the Earth.
Scientists at NASA's Goddard Space Center observe the solar flare. But the CME is moving faster than anticipated. 90 seconds after citizens first see the northern lights, most of the continent goes dark. The magnetic storm sends ultra-high voltage through power lines across North America.
And it creates a really strong magnetic field that induces another current and so on, and the current gets so strong it melts the wire, and then you've got a lot of energy being released, it explodes the transformer.
Giant transformers explode in city after city. All electricity disappears. So do communications, as satellites are burnt out. There are no phones, no television, no radio, no internet.
The whole infrastructure would be damaged. We wouldn't have communications. We wouldn't have so many different things.
And the electricity will not be coming back.
We could damage enough transformers in one storm that would take several years of the entire world's manufacturing capability to replace all of those damaged transformers.
Without power, infrastructure collapses. The first thing to go, water. Without electricity for pumps, city tap water will go dry within a day. The same is true for gas pumps and gas stations. Without fuel, national trucking stops. So do food deliveries to grocery stores. People can't leave the cities because their gas tanks are empty. They can't use their credit cards or ATMs without electrical power and phone connections. No power, no gas, no food, no water. and no end in sight.
Think of totally destroying the power grid of an entire continent. We would be basically put back in the Dark Ages.
And no help is coming, since the magnetic storm has devastated the entire northern hemisphere.
These storms have a planetary footprint. They extend not only across entire continents, but arguably across the entire planet.
It's not just a magnetic storm, it's a magnetic apocalypse.
There would be billions or even trillions of dollars of lost economy.
And that's not the only thing lost.
The consequences and the potential for loss of life are quite large. Perhaps taking out a third to a half of the population of the civilized portions of the world.
Sound unlikely? But that is exactly the conclusion of the National Academy of Sciences report from 2009. A magnetic storm from the sun could wipe out our technological infrastructure, killing millions of people and destroying much of what we think of as 21st century civilization. It's not just guesswork. A solar magnetic storm actually knocked out power to Quebec in 1989, blacking out an entire Canadian province. But that storm was small.
We're seeing storm events over the last 30 years or so that jumped up literally 10 times larger than that 1989 storm.
A new generation of solar satellites has revealed just how big these solar flares are and how vulnerable our planet is.
As society, we are not prepared for a long-term blackout of the power grid.
Can this scenario be prevented? Possibly, but only by understanding one of the most basic forces of the universe and one of the least understood: magnetism.
Magnetism is key to understanding a lot of physics because it affects a lot of things. It affects how stars condense. It affects how galaxies form. It affects how black holes collapse.
Magnetism is everywhere and in nearly everything. It is one of the four fundamental forces of physics, the forces that keep the universe itself together.
Physicists have identified four fundamental forces at play in nature. There's a strong nuclear force that holds atoms together, the weak nuclear force that also has to do with holding together particles and atoms, and gravity, with which we're all familiar, and then electromagnetism is the fourth. Electricity and magnetism are really one and the same thing.
For something so fundamental, magnetism often gets overlooked. Besides holding notes on your refrigerator, magnets rarely show up in an average person's daily life.
Magnetism is not something that we normally deal with. You can't feel a magnetic field. You can run a magnet over yourself and you don't feel a thing. So it isn't part of our daily experience.
The key component of magnetism is that it attracts and repels.
I'm holding here two magnets to illustrate how magnetic fields work and, frankly, how strong they are. Right now, they're attracting one another, and I have to really pull to pull them apart. But they also can repel each other, and I can illustrate it by putting it on this post. If I put the first one down and drop the second one, I really can't push it down. It just bounces.
In fact, the only thing that keeps people from walking through walls or falling through the floor is magnetism. Molecules and atoms are extremely small, and the space between atoms is extremely large. At an atomic level, almost everything is made of empty space.
The distance between the electrons that are orbiting around the protons in the nucleus is fairly immense. It's like this fan. If you let the electrons be the blade and the center be the nucleus, if there's no motion taking place there, you would pass right through things. It's not solid. So why is it solid? It's because the electromagnetic attraction between the negatively charged electron and the positively charged proton, it captures it and it spins around. So if it's spinning really fast, like the fan blades of this fan, representing the electrons around the atom, it bounces right off. That's why you don't fall through the floor and why you can't walk through walls.
It's not the atoms themselves, but the magnetic field that makes matter solid, that keeps a person from walking through walls. Magnetic force attracts and repels along field lines.
You can take a bar magnet and lay a piece of paper over it and cover that piece of paper with iron filings. And the iron filings will actually line themselves up along the field lines coming out of the magnet. And that's a good way to see what the magnetic field actually looks like.
One way to think of field lines is like lanes on a freeway. The southbound traffic never interacts with the northbound traffic.
Electromagnetic field lines are like lanes on a freeway. Cars go down the lanes, down the freeway. And that's why if you look on the surface of the sun, you see these beautiful arcs that represent the field lines where the plasma can flow.
But on the surface of the sun, these field lines are intensely powerful and deadly. In this freeway analogy, imagine if a middle lane was opened up on the freeway between the speeding north and south traffic.
There's no instruction as to who's supposed to go on that lane. You'll get a big mashup right there where the cars, everyone's trying to go on that lane and chaos ensues and there's a big release of energy.
Now imagine if this freeway was on the sun and the cars were 20,000 miles long. The enormous crash fires material off the sun and straight toward our planet. That is a coronal mass ejection. A CME is gigantic, over 10 billion tons of solar plasma. It's the equivalent of 100,000 aircraft carriers traveling at several million miles per hour toward Earth. This is the threat to our planet. A direct hit from a CME is a rare occurrence, but it would be catastrophic for our civilization.
We're literally one big storm away from an engineering disaster.
The sheer size of that disaster has only become clear with new reports from the cutting edge of solar science. Disturbing new information from satellites might help us predict the next deadly blast of a magnetic superstorm. Magnetic solar storms have only recently been shown to be a deadly threat to the Earth. The sun is constantly ejecting material, from radiation to X-rays to solar flares to coronal mass ejections. The reason these ejections don't routinely hit us is that Earth is protected.
The Earth has this huge magnetic field surrounding it. It's all around the thing. And what happens is, if there's a solar flare, a coronal mass ejection, our magnetic field is our savior. It's our armor.
Imagine the Earth as this globe, and the sun is a shotgun. The sun fires off powerful blasts toward the Earth every few days. But the planet has a protective shield, like a sheet of plexiglass that protects a globe from shotgun blasts. It's called the magnetosphere, a gigantic magnetic field generated by the planet's churning core. It extends out 43,000 miles. Just as a ring magnet repels another ring, Earth's magnetosphere repels the magnetized plasma from the sun. 1 billion tons of superheated, electrically charged plasma hits our planet and normally just rolls around it.
The electromagnetic shield of the Earth is a shield. charged particles try to get in, but they bounce against and get redirected by the magnetic field.
Only a tiny piece of the magnetic storm gets caught in the small opening at the planet's poles, where we see it as the northern lights.
Earth's magnetic field redirects energetic particles to the poles of the Earth. And we see that when we see the northern and southern lights. Those particles interact with the Earth's atmosphere and cause it to glow. And it's a beautiful light display.
The magnetosphere can redirect electromagnetic material, which allows life to flourish on Earth. Without it, radioactive particles would likely kill off all forms of life. Fortunately, the field directs away some material, like solar flares, and allows other materials into our planet's atmosphere, like light and heat.
You might wonder, how is it that our magnetosphere protects us from coronal mass ejections, but the sunlight still comes right through, and we have daylight? Well, that's because the coronal mass ejection is mostly charged particles, and it's the electric charge that the magnetic field grabs a hold to and traps. Light has no electric charge, and since it's not a charged particle, it passes right on through the magnetic field like it's not even there.
But where does the planet's powerful magnetic force come from? That can be answered with one of the oldest and simplest of magnetometers, a compass.
I've got a compass here. It's a pretty simple device to tell you which direction is north. It uses magnetic fields, so sometimes it doesn't always point that way, and I want to show you why it doesn't. We're here at a junkyard, and behind me is a huge electromagnet. And when we turn that thing on, what's going to happen? Let's take a look. Wow, compass turned toward the magnet. But when we turn that off, it's going to turn back and point to the north. And what that tells us is compass doesn't point to the north, it points to the nearest, largest magnetic field.
In fact, compasses don't really point to the North Pole. They point to a chunk of rock west of Ellesmere Island off Canada. This is the magnetic North Pole. But the North Pole is not a magnet itself. The magnetic field is actually generated by forces deep within the planet.
Magnetic fields are generated by moving currents, and the Earth is one big moving current. The Earth spins, and the interior of the Earth is molten and liquid. It's kind of like this glass of wine. That's kind of what happens inside the Earth's core. Molten iron in the core swirls around and generates the magnetic field.
Our planet is actually a dynamo, a device that transfers mechanical energy to magnetic energy.
Dynamos. There's one on the Earth, there's one on the sun, and there's one on my bike. As you see, as the wheel turns, it's turning the axle in this dynamo. There are magnets attached to the axles. The magnets are spinning around. There's a coil of wire wrapped around there, and that spinning magnet is inducing an electric field and current into this wire that runs up to this light. And as I spin the pedals, you can see it converts the kinetic energy to electrical energy to light energy.
The key for a dynamo is motion. Moving fluid can create electromagnetic energy, just as much as a moving bike tire. In fact, fluid creates the most powerful magnetic force on the planet in the fluid dynamo called Earth's core. But there's a problem with this ancient dynamo. It can stop or change direction.
Earth's magnetic field is not a stable, static thing. It's changed quite a lot over time.
Like the wine in the glass, Earth's magnetic dynamo can change direction. The North and South Pole can literally flip. Exactly what causes the poles to reverse is not completely understood. All we know is that it happens.
We know that the orientation of the Earth's magnetic poles switches every few 100,000 years.
Ice cores and deep-sea geology reveal evidence that 780,000 years ago, compasses would have pointed south. 50,000 years before that, a compass would have pointed north. It's a recurring pattern on our planet, and it may happen again.
It's almost certain that Earth's magnetic field will change direction again, but we don't know how soon.
In fact, the last magnetic reversal was 780,000 years ago, which is longer than, on average, the field reverses. So in a sense, we're overdue for a reversal.
No one is sure how a pole reversal will affect human life. Compasses will point south. Bird migrations might be disrupted. GPS navigation will be affected. But there is a more disturbing consequence. A pole reversal might mean a period where there is a weakened or no magnetic field on the planet.
The problem is that the magnetic field, when it gets weak, it's no longer an effective shield against particle radiation from the sun.
Imagine the Earth as a globe with a plexiglass shield. Only now, the shield is weakened. A high-powered blast from the sun can do immense damage. When the overdue pole reversal takes place, Earth's protective magnetosphere may disappear, leaving the entire planet vulnerable to deadly magnetic storms from the sun. Solar magnetic storms pose a disturbing threat to life on our planet. On the surface of the sun, a flare begins to boil, bubble, then explode.
It's a horrendous explosion on the surface of the sun, and you have this huge storm, a coronal mass ejection. These ionized particles fly away from the sun at extreme velocities.
These are unprecedented images from NASA's new satellite called SDO, the Solar Dynamics Observatory. Never before has humanity had such a close look at our home star.
The big difference between this observatory and previous observatories is that we're looking at all of the sun all of the time. Previously, we've looked at small areas, not the whole disk.
Launched in February of 2010, the SDO measures magnetism, ultraviolet rays, and even the interior of the sun. Already, SDO has returned never-before-seen close-ups of solar flares, magnetic rain, and tsunamis that ripple across the surface of the sun.
It's like having a DVR. You can go back and you can catch the interesting part, having an instant replay. So we're going to see connections that we've never seen before.
One of the most important connections is that all solar activity is basically magnetic activity.
The key to understanding the variability of the sun is magnetism. We see sunspots, we see filaments, we see explosions, we see coronal mass ejections, big explosions of material into space. The only way to understand how that all ties together is through the magnetic field.
The sun's magnetism is created by the movement of superheated plasma as it ripples across the surface of our home star.
One of the ways in which magnetism is generated is by a moving current. So any flowing, moving charges will generate a magnetic field. The sun is one huge bag of flowing, moving charges.
One of the magnetic phenomena that can actually be seen from Earth is a sunspot.
Now, if you look at the sun and you see a sunspot, it looks like a dark spot. What's really happening is the magnetic field is twisted up on itself in a certain way. It looks kind of like when you pull the drain out of a bathtub and it spirals down into the drain, you create sort of a tornado, a vortex, on the surface of the sun. And you have extremely strong electromagnetic fields there.
A sunspot can lead to something far more dramatic, a solar flare.
There are explosions on the sun. We call them solar flares. Solar flares can be either fairly small, by which I mean the size of an atomic bomb, or they can be as big as 1 billion atomic bombs, all happening at the same time.
Solar flares arc millions of miles above the surface of the sun. These magnetic storms are more than simply intriguing astronomical data. The sun's magnetic field creates a dynamic, ever-changing atmosphere throughout the solar system. It has come to be called space weather.
Space weather is the idea that things that change in space can have effects on us here on the Earth. And how do we measure that? How do we learn to predict it?
Space weather can affect satellites surrounding Earth. High-powered X-rays from a solar flare can cause millions of dollars of damage in communications and navigation satellites. Astronauts on the shuttle and space station have to know the space weather forecasts to avoid deadly radiation during a spacewalk. These are the kinds of problems the Solar Dynamics Observatory is designed to predict.
Forecasting space weather is one of our big challenges. We want to learn how to do it better. Now, most of us don't really trust weather reports too much, a little bit, but not too much. We're way behind that. We're not anywhere close to being able to do that yet with space weather.
Are there regular patterns to space weather? That's exactly what Benjamin E. from Cleveland, Ohio wanted to ask the universe. Benjamin emailed us, "Can science predict solar flares and CMEs before they begin?"
Interesting question, Benjamin. We'd love to be able to predict exactly when giant coronal mass ejections occur. It turns out that roughly every 11 years, there's a maximum in the number of sunspots, coronal mass ejections, solar flares, and associated activity. We can predict roughly when that'll occur. However, we can't predict when any particular sunspot group or coronal mass ejection will occur.
By far, the most powerful examples of space weather are coronal mass ejections. They are connected to the solar cycle, peaking during solar maximum, with as many as 2 or 3 per day. They begin with beautiful solar storms, witnessed by the Solar Dynamics Observatory in full color. A hurricane of magnetic fields will grow and swirl, sending arcs and plumes of flaming plasma thousands of miles over the surface of the sun.
Sometimes these structures are stable for days or even weeks at a time, and then something will happen to trigger a release of the coronal mass ejection. And all of a sudden one part will lift off, and then there'll be a huge lift off, and then it will go off into space.
The gigantic burst of charged plasma heads toward our planet, where it usually flows harmlessly around our magnetosphere. But there's a problem with Earth's magnetic field. It's beginning to change. And the worst-case scenario for Earth's magnetic future is the cold, dead surface of Mars. Magnetic storms may well be able to bring civilization to a standstill. If it weren't for the protective power of our planet's magnetosphere. If Earth has a magnetic field, do other planets? It's a vital question, according to NASA, because other planets' magnetic properties may reveal the future of Earth.
1, 0, liftoff. We have a liftoff. 32
Only with the beginning of the space programs in the 1960s have we been able to detect the magnetic fields of other planets. And the discoveries are surprising.
All 4 of the giant planets, Jupiter, Saturn, Uranus, and Neptune, all have actively generated magnetic fields today. Jupiter's magnetic field is the strongest in the solar system. Its surface field is about 10 times the strength of the Earth's.
Jupiter's magnetic field stretches over 4 million miles from its surface, and it performs the same function as Earth's field.
We see northern lights on Jupiter and Saturn, which is exactly the same interaction that we have northern lights on Earth. It's particles from the sun being focused to the poles of those planets by those planets' magnetospheres, and they light up the atmosphere just like they do on Earth.
But closer to the sun, planetary fields are mysteriously less common. Mercury has a very weak magnetosphere, about 1% of Earth's. Venus has virtually none. And the most mysterious of all is the red planet, Mars.
In the late 90s, the Mars Global Surveyor spacecraft, which was in orbit around Mars, had a magnetometer aboard. That magnetometer found that Mars does not have a global magnetic field.
But the Mars surveyor found evidence of small magnetic fields scattered on the face of the planet. NASA believed it was paleomagnetism, an ancient remnant from a period billions of years ago. Did Mars once have a magnetic field rivaling Earth's? And if so, what happened to it? Fortunately, we don't have to go to the red planet to investigate, because pieces of the red planet are already here.
We actually have samples, rocks from Mars. They're meteorites. They were blasted off of Mars by an asteroid or comet impact millions of years ago. These rocks wandered around in space, and then some of them landed on the Earth randomly.
One of these Martian meteorites is actually famous. ALH 84001. Some scientists have suggested it contains the remains of ancient Martian life forms. Whether or not this proves true, this piece of rock may answer the question of Martian magnetism.
ALH 84001 is the oldest known rock from any planet, and it is a unique sample from Mars. It lived through the earliest epoch of Martian history. So this sample has all kinds of fascinating records in it.
MIT's superconducting quantum microscope, or SQUID, is one of the most sensitive magnetic detection devices on Earth. A sample from the Martian meteorite gives up startling results under the SQUID lens.
We showed that this rock is magnetized, and the magnetism, the paleomagnetism, has been very precisely dated to be about 4 billion years old.
Beneath the surface of the meteorite is the ancient record of Mars' magnetosphere. 4 billion years ago, a strong magnetic field was generated by churning magma in the planet's core.
Early magnetic Mars was a fundamentally different place than the one we see today. The atmosphere, we think at that time, was much thicker than it is today. There was probably water flowing on the surface. Temperatures were warmer. So it was much more Earth-like.
Then, mysteriously, Mars died. Temperatures dropped. Water vanished. The atmosphere disappeared. What happened?
Mars' magnetic field died sometime around 4.1 billion years ago. What's really fascinating about that is it seems to be roughly coincident with the time when Mars began to change from an early warm, wet state to its current cold and dry conditions.
One hypothesis for why Mars' atmosphere disappeared was because it didn't have a magnetosphere to help protect it. So the solar wind was constantly stripping away parts of the Mars atmosphere.
Without magnetic armor, a coronal mass ejection would bombard Mars' surface, a magnetic hurricane that would tear away the planet's atmosphere.
Suddenly, the atmosphere was losing large quantities of gases like oxygen, argon, nitrogen. The atmosphere got thinner over time. Liquid water stopped being stable on the surface, and Mars kind of went into a stasis, a cold, dry stasis.
But could it happen on Earth?
Certainly, at some point, the Earth's magnetic field will shut down, but that's a long way off. A more immediate issue is when will the Earth's magnetic field reverse?
As we saw earlier, our planet reverses its field every few 100,000 years, and we're overdue. When the Earth's magnetic field reverses, the process may leave Earth without a protective magnetosphere for a period of days, or even longer. This could lead to the very real possibility of the Mars scenario.
We're going to see magnetic storms like we've never really experienced since modern civilization.
But we don't need a planetary reversal to wreak havoc. Experts say our entire society could be destroyed by a magnetic storm. Planetary disaster might be avoided, but steps must be taken soon. And the clock is ticking toward magnetic apocalypse. Magnetic storms are some of the most powerful forces in our solar system. And they've been nearly completely overlooked by science. These storms have damaged our planet before. In 1989, a solar flare hit North America, wiping out power to Quebec and the surrounding area. 6 million people were without power in the middle of a cold Canadian winter. Electricity was restored within a day, preventing a greater catastrophe. But the Quebec storm was a small one. A far greater storm was actually recorded in 1859. Northern lights were seen as far south as Cuba. Telegraph lines stretching across America hummed and sparked as a massive power surge shorted them out.
This may have been one of the largest geomagnetic storms that has ever occurred. Literally 10 times larger than what caused the problems in the North American grid in 1989.
New data from SDO and other observatories show that these massive solar storms are far more common than we once thought. What would happen if the same giant storm from 1859 hit our planet today? The disaster would begin with a sunspot erupting on the solar surface, firing billions of tons of material directly at Earth. In 8 minutes, gamma rays and X-rays wipe out most satellites. Our wired society is now blinded. No GPS, no plane navigation, no satellite or cable television.
We have hundreds and hundreds of satellites in orbit. And on average, each of those satellites cost $500 million. Well, there's hundreds of billions of dollars right there that's gone.
Within 8 to 16 hours, the great mass of ejected solar material hits Earth's magnetosphere, overwhelms it, and blasts across the face of the planet.
Infrastructure will start seeing large induced currents starting to flow through large power lines.
It's going to make power transformers explode all across the country.
When the transformers go, Every piece of electrical equipment in America goes with it.
It's a critical infrastructure, probably the keystone infrastructure. If you take electric supply away, virtually all other infrastructures will fail either immediately or within just a few days.
Where does your drinking water come from? It needs electricity in a lot of cases to pump the water up, so you're not going to have drinking water. You're not going to have lights unless you have your own generator. And then when the generator runs out of fuel, well, if you run down to the gas station to get some more fuel for the generator, there's no electricity to run the pumps.
The electricity will not come back on because the transformers will be too damaged to repair. They will have to be completely replaced, and that is not a simple proposition. It takes at least 6 months to build a single transformer from scratch. That means no electricity, no water, no fuel, no banking for 6 months. For major cities. Smaller cities will take longer. To rebuild the entire grid might take over a decade. The cost of repair is staggering. The cost in human lives, disturbing.
There is no way that we could sustain a 300 million population in this country with large disruption of that scale.
Some estimates suggest that a large magnetic storm could lead to the death of 1/3 to 1/2 of the population of the developed world. That's 100 million deaths in the US, 250 million in Europe, 1 billion in Asia. Lives lost to the power of a magnetic storm.
Up until this time, this sort of disaster has truly been incomprehensible.
Can anything be done to prevent this type of destruction? Experts are trying to plan for that now. With better observation of the sun's explosive magnetic surface, as well as designing shields for cables and creating surge preventers for transformers.
We now have to think in ways of retrofitting design changes into those grids. We're still at early days of trying to figure out how to harden the infrastructures against these.
The apocalyptic power of a magnetic storm reveals just how essential magnetism is in our lives and in the very universe itself.
Electromagnetism is the most important thing that you can see that's driving our daily lives.
I think people don't think about magnetism because it's kind of like a fish in water doesn't think about the water. It's everywhere. It holds everything together. It holds the atmosphere, the action of breathing, the action of seeing as an electromagnetic interaction.
Magnetism is a simple force, one of the 4 most basic forces in the universe. It can become a child's toy. It holds our molecules together. And if we're lucky, it protects our planet from the vast powers of the sun. To the inhabitants of Earth, it is one of the most overlooked forces in our universe. Yet magnetism gives and can take everything.